spaces built out of patches that look like flat space with some bosonic coordinates and some fermionic coordinates, and some local differential which maps one into the other, and then coordinate transformations which preserve the differential. This is actually the most general setup you can think of. And then some of these derived geometries will turn out to be the same as some simpler, some real standard geometries. But they might be a simpler description of those geometries. So for those constraint systems, I would guess that the BRST quantization consists of finding the correct derived geometry, which is equivalent to your constraint system, but is simpler. And the fact that there is a lot of freedom in doing so is just because there is a lot of freedom in deforming your BRST constructions by adding Q-exact things all over the place. I mean, that freedom is precisely what makes the BRST quantization powerful in a sense, because you can make whatever choices are convenient for you and then show that they don't matter. Okay, any other questions? I would like to discuss a few more facts about boundary conditions in quantum field theory in general and boundary conditions in two-dimensional conformal field theories. So let me start by reviewing again this statement I made that for a one invariant boundary condition, the components of the stress tensor with one leg along the boundary and one leg perpendicular to the boundary have to vanish. So suppose I have some flat metric. And I do a combination of a diffeomorphism and a Weyl transformation. Infinitesimal ones. So the metric remains flat if this vanishes. So there is a condition, there is something called a conformal clean vector. Which is a vector field which just satisfies this equation. So it's a vector field such that the AVB plus the BVA plus some arbitrary multiple of the identity matrix vanishes. So these are the combination of diffeomorphisms and Weyl transformations which leave the metric flat. So you can write down a conserved charge and a conserved current for these transformations, which is just T mu nu or TAB BB. Why? Because if I do the divergence of this current, I get two terms. I get the divergence of the stress tensor, it vanishes. And then I get TAB, DAVB. But if T is symmetric and traceless, and this holds, then this vanishes. Because if it's symmetric, you can symmetrize this, map it to that, and then you get the trace of the stress tensor which vanishes. Now, in order for a boundary condition to preserve these symmetries, the normal component to this has to be a total derivative. I was mentioning yesterday that the influx of charge into the boundary must be equal to the amount of charge which is appearing or disappearing from the point of view of some boundary currents. But the normal component of this looks like this. And translation invariance tells you that this was the same as the time derivative of some boundary stress tensor. And you see that this is a function of time, it's a function of the direction parallel to the boundary. This is never a total derivative. Right? If I integrate by parts, I'm going to get the divergence of V. But the divergence of V is precisely the same as F. So it tells you that a boundary condition can be Weyl invariant only if this guy vanishes, or if your Weyl transformations vanish at the boundary. But then it's not Weyl invariant. So if you want invariance under all Weyl transformations and all diffeomorphisms that leave the boundary where it is, then we need this condition to hold.
Sorry, what's lowercase t again?
So remember, if I just had translation invariance, in principle, I could have a weaker condition. Where this at the boundary is a total derivative of a boundary stress tensor, whose non-conservation compensates for the influx of energy and momentum. But this doesn't work for Weyl symmetry, for general conformal transformations. So this is the condition that you need for Weyl invariant boundary condition. Okay. So that's point number one. Mm-hmm. Yes.
But when you say the condition you need for Weyl invariance, is it sufficient to?
I mean, it's sufficient and necessary. This is fully equivalent to Weyl invariance on the boundary condition. Okay, so this is statement one. And it's true in general dimension, not just in inch dimensions. The statement number two I wanted to make was about something called Champerton bundles in the string theory textbooks, which is sort of related to the fact that you can put you can put in your theory several different D branes. Mm-hmm. Yes.
Sorry, I'm actually still stuck back here. Can you just explain one last time how that condition that you've boxed arises from what you wrote at the bottom?
Can we agree that it's sufficient?
No, sorry.
So I'm considering a boundary condition, right? I'm looking at vector fields which leave the boundary where it is, because otherwise clearly I could not have a symmetry if my boundary is moving around. So V at the boundary, so V at the boundary has to be parallel to the boundary. So V perpendicular vanishes at the boundary. So this only has parallel components. So if T perpendicular parallel vanishes at the boundary, then clearly I have my condition, right? That the normal component of this vanishes.
Why do you want to normal?
Why is that the condition we want?
Well, I want it to be a total derivative. If it vanishes, it's in particular a total derivative.
You want the whole. Oh. Why do you want it to be a total derivative?
Sorry?
Why do you want it to be a total derivative?
So I have a current, right? This current, you can call it JA, right?
Yeah.
And I want the J perpendicular at the boundary should be a total derivative. So that the amount of charge that flows into the boundary can be compensated by the lack of conservation of the boundary current. I mean, why is that conserved currents give you conserved charges? How do you define a conserved charge associated to conserved current? That's right. So in two dimensions, I take J0 and I integrate it over dx1 of the whole space. And if I try to change the location in time of this operator, right, I get the integral of the 0 J0 dx1. And if this is a conserved current, this is the same as the integral of minus the 1 J1 dx1, which is the total derivative and vanishes. Now, if I have an actual boundary here, though, then this does not vanish, right? This is the value of J1 at the boundary. So this by itself does not give me a conserved current. I have two possibilities. Either this just vanishes by the boundary conditions, then I'm done. But if this does not vanish, what I can do is I can add here a boundary current which just lives here. Then here I get an extra term. And I'm happy as long as this is a total derivative.
Okay.
So I want to do the same thing here, where J is this. So here's this. So I need the perpendicular component of this to be a time derivative of something for all choices of V that satisfy the conformal killing equation.
Are you making any assumptions about whether the boundary is time-like or space-like?
No. That's why I didn't call this 0 and 1. It's just direction parallel and perpendicular to the boundary. And so when can you write this as a total derivative? If I take V to be constant, then I need T itself to be a total derivative, right? Now remember, so here V, I can take it to be really parallel because the perpendicular component vanishes at the boundary. So I can write something like that. But then I can take V to be dependent on the position. I can integrate this by part. But this is precisely F at the boundary. So in F, there are definitely conformal killing vectors for which F is non-zero. For example, a scale transformation has V parallel equal X parallel. So this divergence is literally 1. And so this has to vanish. So there cannot be any boundary stress tensor. There can only be this condition. Okay? Very good. Now, and incidentally, this works for all conserved, other conserved currents. So if you have a theory which has a U1 symmetry and is Wall invariant, you can show that there cannot be a boundary current for the U1 symmetry either, by just doing Wall transformations of the basic constraint. But anyway, remembering how the currents transform under Wall transformations and so on and so forth. But we don't need that. Okay, so the other statement I want to tell you about dimensional quantum field theory concerns the possibility, concerns the description of Champaton bundles. So when you read a textbook like a Polchinski, it sounds like the Champaton bundle is something that you only need in string theory. That's not true. Champaton bundle is just another name for some very basic fact about quantum field theory. That you can take direct sums of quantum field theories, you can take direct sums of boundary conditions, there are some interesting operations on quantum field theory, in quantum field theories or on defects in quantum field theories. So in particular, the following fact is true. Suppose I have some theory T, change dimension, and some boundary condition, B1. So this boundary condition tells me what to do, classically tells me what to do with the fields of T when they approach the boundary. To be, if you want the correct statement, that it's some elliptic boundary condition for the equations of motion. Anyway. And suppose I have another boundary condition, let me call it B2. Then I can always define a new boundary condition, which you can call B1 plus B2. Where essentially, classically, the fields of T have a boundary condition which says either the fields satisfy this constraint or they satisfy this constraint. If this boundary condition tells me that some field at the boundary goes to 1, and this tells me that some field on the boundary goes to 2, I can have a boundary condition where the field is allowed to go to either 1 or 2 at the boundary. And that's fine. It's perfectly possible to start it in, a single boundary condition, deform it by some relevant operator at the boundary, and do an RG flow which lands on direct sum of 2 boundary conditions. So this notion is really part of quantum field theory. You encounter it all the time. For example, if you study topological order, you find something called the direct sum of anyons. If you think about anyons as line defects in your theory, direct sum is just this direct sum. Anyway, so what are the properties of this direct sum? One of the properties is that if I put my theory now on a strip with boundary condition 1 and boundary condition 3, this gives you some space of states labeled by the choice of boundary conditions at the two ends. If I do the same with B2, I get a different space of states. Then the statement is that if I look at a space of states on a strip with boundary condition B1 plus B2 at one end and B3 at the other end, this is the direct sum of the Hilbert space with boundary condition 1 and boundary condition 3, and the Hilbert space with boundary condition 2 and boundary condition 3. Or if I study correlation functions of the theory in the presence of boundary condition B1 plus B2, they're just going to be the direct sum of correlation functions in the presence of this boundary condition and correlation functions in the presence of this boundary condition. So this is what the direct sum of boundary conditions is. So you see that if I have a situation where I have a direct sum of a lot of boundary conditions BA and a lot of boundary conditions BB, my Hilbert space will start looking like a matrix of Hilbert spaces. Right? Because it's the direct sum of Hilbert spaces labeled by two labels. And the analogy with the matrices is actually quite important when you start thinking about calculations on interesting surfaces. So suppose I look at a surface which has 3 segment asymptotic regions. So I can put some state here, leading from boundary condition A to boundary condition B. See? Just, right. So suppose I put everywhere this sum of boundary conditions. So here I can take a state in the Hilbert space that goes from boundary condition A to boundary condition B. And a state in the Hilbert space which goes between boundary condition B and boundary condition C. As you can see quite clearly, I'm going to produce a state. This picture will produce a state which lives between boundary condition A and boundary condition C. So these sort of pictures give you something that looks like matrix multiplication. The indices just connect pairwise. Which is, well, anyway, we'll see more about that. Finally, I would like to discuss the notion of boundary local operator. So, when you do correlation functions in a quantum field theory, the basic questions you can ask are involving inserting some local operators at some position in your space-time. The space of local operators is some, there is some vector space of local operators, which are the list of all possible questions you can ask in that neighborhood of space-time. And we learned that there is a state operator mapping in wide-invariant theories, where the space of bulk local operators is isomorphic to the Hilbert space of the theory compactified on a circle. Right? Are these statements clear? Now, if now you study a theory which has a boundary, then you can ask questions near the boundary, at the boundary. The list of questions that you can ask at the boundary are completely different from the list of questions that you can ask in the bulk. So there is a completely different space of boundary operators which sort of interpolate between boundary condition 1 and boundary condition 1, which live on boundary condition 1. If you choose boundary conditions, you can even consider boundary changing operators. So operators with the property that the choice of boundary condition changes as you jump across. So yes, if you have some collection of boundaries, there will be spaces of boundary local operators, which again look like a matrix because they carry two labels. And of course, they also multiply as matrices because I can only combine an operator from boundary 1 to boundary 2 with an operator from boundary 2 to something else. But importantly, there is again a state operator map. So the boundary operators between boundary 1 and boundary 2 are isomorphic to the space of states on a segment with boundary conditions 1 and 2. I mean, what I was calling just H V1, V2 here. So there is a state operator map for boundary local operators, which allows you to trade states on a segment and boundary local operators. So this allows us to convert calculations like these to calculations on a disk, say, or another compact surface with insertions of boundary vertex operators. The same way as we mapped complicated surfaces with tubes, semi-infinite tubes, to compact surfaces with bulk local operators, we can replace semi-infinite strips with boundary local operators. Okay, I think this is all the general lore about boundary conditions in quantum field theory which you need to understand what's going on. Notice that at the time where people were defining string theory, a lot of these notions are not so clear. And actually the study of deep branes has forced people to understand better boundary conditions in quantum field theory. Okay, now we can specialize to our bosonic string. Yes?
Is there some group that maps these Hilbert spaces to another?
If these boundary conditions are different, there is no relation between these Hilbert spaces at all. Now, of course, if I have a picture like this, so you have boundary condition 1, boundary condition 3, boundary condition 2, boundary condition 3, and boundary local operator here. This will act as a map from this Hilbert space to this Hilbert space. And also, nobody said that these boundary conditions have to be different. The funny thing is that the direct sum of boundary conditions give you something new, even if B1 and B2 are the same. So there is a boundary condition B1 plus B1, which is not the same as the boundary condition B1. It imposes the same boundary conditions on the fields, but there is sort of a two-dimensional vector space, auxiliary vector space, which is living on top of the boundary, decoupled from the rest of the theory. So in that case, if I look at the boundary condition B1 times B1, so that can be really sort of thought of as a tensor product of a vector space, two-dimensional vector space, and B1 itself. So your fields, bulk fields, only see this. Your boundary local operators are matrices acting on C2, 2 by 2 matrices acting here, combined with local operators here. So and then say this properly. So in the same way as you can take a bulk theory and deform it by some relevant operator to get energy flow to some other theory. When you deform your boundary conditions, you deform it by boundary local operators. And there are plenty of situations where adding these extra degrees of freedom give you new flows that were not available before. There are some very nice examples like the Kondo problem you've ever encountered, which is a very classical problem in condensed matter physics, where you have some degrees of freedom interacting with a local spin. So you have your bulk degrees of freedom, and then you put just a spin at the boundary and you turn on a coupling. Something like a polymatrix acting on the spin, contracted with some current or something of the bulk theory. Some boundary operator, or something like that. That will give you energy flow, which is just not available if I was talking about B1 itself. and gives new physics. Because it's describing the coupling of the bulk theory to a spin degree of freedom living in situ.
Say your boundary is a direct sum of BA and BB.
Yes.
Does that guarantee you an operator that a boundary condition changing operator that takes you from BA to BB?
In a wide invariant theory, yes, because of this isomorphism. So if there were no boundary changing operators, then it would mean there would be no states on a segment in boundary condition 1 and boundary condition 2. That would be quite absurd. Because, for example, I can consider a geometry like this. Let me say it properly. Imagine taking the segment very, very long, right? It's hard to. I cannot imagine any situation where, in quantum field theory, I construct a setup where there is no Hilbert space at all. You can easily run into a contradiction. But also, what I wanted to say was this. Suppose I have a surface that looks like this. There is something complicated going on here, something complicated going on here. There's boundary condition 1 and boundary condition 2 here. So I should be able to insert a complete set of states here and cut. So essentially, if there was no Hilbert space associated to a segment, you would conclude that any correlation function where the two boundaries occur vanish. No matter how far are these boundaries. Right? That's problematic. The quantum field theory has properties like clustering that tell you that if you do two local things far away from each other, the result is just as the product of doing this and doing that. So that vanishing would violate clustering, at the very least. So essentially, the only situation where I can think of that happening is if the bulk theory itself is a direct sum of two theories. Meaning, suppose I take something like an Ising model where there is some spin that can be up and down, right? And I suppose I'm low temperature. So I have two vacua, the all spin up vacuum and the all spin down vacuum, right? Suppose I flow all the way to the bottom of the RG flow. So I get two super selection sectors essentially, because the domain walls which allow me to go from spin down vacuum to spin up vacuum have an infinite tension in the far infrared. Now, if you consider boundary conditions which set the spins to be either up or down, clearly there will be a problem. If I try to have a segment where boundary condition is set to be, the spin is set to be up on the left and down to the right, and the domain walls between spin up and spin down are infinitely massive, I'll never get a normalizable state on that segment. So barring that situation where I really have two different theories added up, but not talking to each other, this cannot happen. Okay, sorry for the parentheses, but I cannot resist quantum field theory questions. So, where was I? Yes. I would like to discuss now boundary conditions for scalar fields, for the x's which describe the motion of the string in space-time. If I have just a single x, as I was mentioning yesterday, the stress tensor looks like the normal derivative of x times the parallel derivative of x. And so pretty much the only thing you can do is, well, it's not really the only thing you can do, but almost the only thing you can do is to set either this to 0 or this to 0. So there are two natural free boundary conditions. One is called Neumann, which sets the perpendicular derivative of x at the boundary to vanish. And the other is called Dirichlet. And what this does is that fixes x itself at the boundary to have a certain fixed value. So Dirichlet boundary conditions secretly come in a family, depending on this value. Of course, if x is constant at the boundary, in particular, the parallel derivative of x vanishes. Now, if you have multiple scalar fields, the possibility proliferate. So one obvious thing you can do is to just say, I take Neumann boundary conditions for some of the scalars, Dirichlet for some of the other scalars. So this is usually called what do you call it, a flat DP brane. Where you take, say, the first P+1 fields to have Neumann boundary conditions, and the remaining fields to have Dirichlet boundary conditions. So intuitively, this DP brane tells you that the string, the endpoint of the string, has to lie on a certain submanifold of spacetime, a certain hyperplane of spacetime, because the position of the endpoint is fixed in these directions and free in these directions. For example, a zero brane would look like just sort of a straight line in space-time on which your strings can end. Now here I took time to be one of the Neumann directions. So this extends in time and sort of gives you, as I was anticipating, it will end up giving you a very heavy object that you just place there and interact with the strings. It's also possible to put Dirichlet boundary conditions on time, which would mean that sort of you have an instanton. Well, so strictly speaking, this would look like a local operator in space-time. You modified your string theory at some location. But in the same way as this is actually secretly dynamical, this location is also secretly dynamical. So what you actually have to do is sort of integrate these over the whole space-time. And so it's essentially giving you some correction to the action of your string theory, some instanton correction to the action of your string theory. And I call it instanton because very literally the way this contributes to your scattering amplitudes is that you have your scattering amplitudes without the instantons, and then there is some correction from this, which is suppressed by a factor of e to the something over G string. So it's non-perturbative from this point of view. So there is this general law that D-branes are telling you something non-perturbative about string theory. They don't tell you everything non-perturbative. There are presumably other non-perturbative corrections that go like e to the 1 over G squared. But they tell you something still important about the non-perturbative properties of the theory.
I don't understand what does it mean with a small x and a capital X?
So capital X is the dynamical field.
Yes.
Small x is a number.
Is the coordinate?
It's a fixed number. It labels that boundary condition. It tells you the coordinate where you place this D-brane. Momentarily, we will find some open string states which describe fluctuations in the positions of the brane. So later on, this becomes an actual field living on the D-brane. Correspondingly, as I said, there are many more boundary conditions than this. Let me give you an example. I could modify Neumann boundary conditions and as long as this is antisymmetric, this would still vanish. Because I contract this with the perpendicular mu. And so that is contracted on a symmetric vector tensor, so it vanishes. If you look at what this does, you're sort of turning some kind of electric field that is felt, that lives on the D-brane and is felt only by the endpoints of the D-brane, of the open strings. And in fact, we'll find that the open string spectrum includes a gauge field. Or you can have boundary conditions where the shape of the D-brane is not a straight line, but some general submanifold spacetime. All of those boundary conditions are not free. They involve expressions which have polynomials in the fields, or worse. These are sort of the most natural free boundary conditions. Maybe also this when this is a constant. But if you try to make this a function of position, clearly it's not free anymore. Then there is a possibility of wild anomalies, there is RG float, there is beta functions for the boundary couplings, for the boundary conditions themselves, which give you an effective action for the open string modes, etc., etc. But we'll have no time to discuss that. What I want to do in the last 15 minutes is sort of discuss the two simplest configurations that you need to understand for thinking about D-branes. Analogous to the calculations we did on the cylinder at the beginning of the lectures. So one possibility is that you can put a boundary condition at some fixed time on the worksheet. You can ask which state is created by having a boundary at tau equal to 0. So here I put some boundary condition B, and this picture gives me a state called usually the boundary state. So this calculation will tell you, among other things, which closed strings are sourced by the D-brane. And the other calculation you can do is to compute this Hilbert space on the segment. Look at the way the BRST charge acts on it. Look at Q exact, Q close modulo Q exact states, and so find the spectrum of open string states. Now, I think I'll leave this calculation as an exercise. It's not too bad. So essentially, you want to find a state which imposes the boundary condition that the tau, say, suppose we do Neumann for simplicity. Right? Then I need a boundary condition that the tau x at the boundary vanishes. Right? So you can look, what you can look for is some state B with a property that the tau x evaluated at time equal to 0 in generic position, acting on this state equals to 0. So you expand this in Fourier modes. Something like that. And you find that B has to live in the part of the spectrum which has 0 momentum, and it has to be some kind of coherent state that is annihilated by this combination. There's probably a minus somewhere that I forgot. Yes. In particular, doing this, you can find that the D-brane sources the sort of gravitons that you would expect from a localized object sitting in this position in space-time. But it also sources all sorts of string states. So it sources all the string states. Which in particular suggests that the intuitive geometric description of this as something sitting at some point in space-time might break down if I try to bring in other D-branes which are close enough. See, if I source a closed string state which is massive, the field sourced by the D-brane would decay exponentially fast in a way controlled by the mass of that state, of the string state. Right? If I have a massive scalar field, say, and I put a source for it, or a massive vector field, put a source for it, you get it sources a background which is exponentially decreasing in space. So you can imagine that as long as your D-branes are far enough, it will be fine to just think about the way they source the gravity. Because, the other massless field, they're the only one who will let them talk to each other. But when I bring them close enough, all these other things, the effect of all the other closed string modes will matter. So something nice, something peculiar must happen when I bring together two D-branes. And this peculiarity is reflected in the fact that the degrees of freedom of the D-branes, when they get close to each other, become matrices instead of just being, you don't just have the degrees of freedom of this brane and the degrees of freedom of this brane. When they get together, you get open string states, which are matrices now, 2 by 2 matrices. Yes?
Could you just explain that point again about that?
I will.
Mm-hmm.
So, let me just discuss the open string spectrum for a second. Then we discuss how it changes when I have multiple D-branes. So, I'm sorry, just because I have 10 minutes and I've been slower than I thought. So I can answer also questions after the lecture. So, how do you compute the spectrum of states on a segment? Well, as long as your boundary conditions are free, what you do is to just write down, again, the expansion in modes of your field, satisfying the boundary conditions. For example, if you have Neumann on both sides, you get something like this. So what I'm doing is I'm writing down the most general Fourier series, which is compatible with requiring the sigma x at 0 and the sigma x at pi, say, if I take this to be with pi. And then you quantize it. You find one tower of oscillators and a zero mode, and a pair of zero modes. So the Fock space of the scalar field with these boundary conditions will give me a bunch of momentum ground states and oscillators built on them. I mean, a Fock space built out of oscillators. The difference is that there's just one oscillator. You don't have an A bar. You just have one A. Somehow the boundary conditions glued together identify A and A bar. And so on and so forth.
So are we no longer allowed to impose that the correlation function of the stress energy tensor matches?
Oh, yes, we are. So we can also write down the stress tensor and expand it out. And you find that there is a sum of modes. What's happening is that somehow T and T bar are expanded in the same modes. So instead of getting two separate collection of conditions for the heuristic invariance, we just get one collection. We want states which are intuitively annihilated by the positive modes of L and are eigenvalues of L0, with eigenvectors of L0 with eigenvalue 1, and so on and so forth. One important point is that L0 acting on these states is 2p squared instead of being p squared over 2, because of some changes in normalization. So now if you look at the string spectrum, you find things like an open string tachyon with p squared equal to minus 1/2, to 1/2. And then you find something which has a single space-time index and is massless. And there's a gauge symmetry where epsilon goes to epsilon plus lambda p. So you find that there is a photon. And then there are a bunch of massive open string modes. Now the open string tachyon is just there, is a bit less bad than the closed string tachyon actually, in the sense that there are some ways we can follow the decay of this tachyon. There are ways to convince yourself that as long as you ignore the closed string tachyon, the open string tachyon is just telling you that this D-brane is unstable and it wants to decay to nothing, to a situation where there is no D-brane. But now, suppose I have a direct sum of Neumann boundary conditions. So I sort of Cn n copies of the Neumann boundary condition on one side, and n copies of the Neumann boundary condition. So I put n D-branes, n space-filling D-branes. What's going to happen? Well, all that happens is now I have little indices which tell me that this was the state going from brane number A to brane number B. So you get n squared copies of this whole spectrum. You get n squared tachyons, n squared gauge fields, n squared massive modes at each level, and so on and so forth. And it turns out that these are not just n squared U1 gauge fields. They're not just n squared photons. Instead, they are n squared gluons, meaning it's a UN These are UN gauge fields. So all the open string modes are matrices, and they're all charged under these gauge fields for the UN gauge group. You can repeat the exercise for Dirichlet boundary conditions or for situations where you have some Neumann, some Dirichlet. The main point is that when you do the analysis for Dirichlet boundary conditions, you don't have momentum at all. So what happens is that now you have only if you have something like that, a DP brane, you're looking at the spectrum of open strings attached to this DP brane. Now you have momentum modes which are only parallel to the brane. Which kind of makes sense. The open strings attached to the brane can move along the brane, but they cannot go away unless they become closed strings. And when you look at the massless modes, now I have both objects which have indices parallel to the brane, which give me gauge fields living on the brane. But I also have objects with indices perpendicular to the brane. And those represent the fluctuations of the brane, right? If I want to, if I have an object which extends along some directions and is fixed along some directions, the fluctuations are controlled by fields which live in these perpendicular directions. So these modes, these massless modes, correspond to making these guys dynamical. The gauge fields correspond to this sort of deformations of the boundary condition. This is literally the field strength of those gauge fields. Okay, and another thing you can check is that when you have 2D branes that are localized in space-time, like 2D zero branes, and they're well separated, then the mass of the open string stretched between them becomes very large. So somehow so when the 2D zero branes are far enough, the open strings stretched between them are very massive. They're negligible. When you bring them close, on the other hand, they become important, become light. So there is this very funny phenomenon that if I have 2 separated D branes, they each have their own position fields and U1 gauge fields living on them. But when I bring them together, the U1 and U1 gauge fields enlarge to a U2 gauge theory. And the position fields become matrices, which is very bizarre. Right? Why would the position of ND branes be described by an n by n matrix? So what happens is that if you look at the equations of motion for these fields that describe the motion of these branes, there is a potential, which is something like the commutator of 2 of these positions squared. So the low energy configurations are situations where these matrices are simultaneously diagonalizable. And the eigenvalues tell you where the different D branes are. So the separating 2D branes is kind of a Higgs mechanism. You have U2 gauge fields, you have a scalar field living in which is a 2 by 2 matrix. You give an expectation value to the scalar field, which is diagonal. And this Higgses the gauge group from U2 to U1 times U1. And Higgses the whole, so all the fields which are off diagonals become massive, which are mass controlled by the separation, by the difference of eigenvalues. So it's kind of funny that something so nice as the Higgs mechanism appears when you study the separation of D branes. Okay, so What else should I say? I don't think I have anything else that I can say in -2 minutes. So let's stop here. And if you have any questions, you can come to the board.